Humanity's exploration of the cosmos began with a simple sense of wonder while gazing at the stars. In the dim light of antiquity, the flickering stars and the cyclical patterns of the sun and moon sparked endless imagination among our ancestors. They used primitive observations to sketch the earliest cosmic maps. From Babylonian clay tablets and ancient Greek philosophical texts to Chinese oracle bones, we find the first records of celestial motion. At that time, it was widely believed that Earth was the center of the universe, with all celestial bodies revolving around it. This was the geocentric model, a concept that lasted for millennia because it was intuitive and aligned with human sensory experience. We stand on a seemingly motionless Earth while the heavens appear to rotate around us. This model, rooted in early philosophy and religion, was further refined by Aristotle, who envisioned a universe of concentric spheres where stars and planets were fixed to transparent crystalline shells. Later, in the 2nd century, Ptolemy introduced epicecles and difference to explain the complex retrograde motion of planets. While this intricate geometric construction could predict planetary positions with relative accuracy, it made the cosmic model increasingly cumbersome. Despite its complexity, the geocentric view dominated Western thought for over 1,000 years. However, as observation precision improved, the model's inherent contradictions became impossible to ignore. In the 16th century, a quiet revolution began when Nicolaus Copernicus proposed a subversive idea: the Sun, not the Earth, is the center of the universe. His heliocentric model simplified the explanation of planetary motion and opened a new door for human understanding. His work, On the Revolutions of the Heavenly Spheres, challenged deep-seated beliefs and acted as a spark for future scientific inquiry. Following him, Johannes Kepler analyzed the vast observational data of Tycho Brahe and discovered the 3 laws of planetary motion. He corrected the notion of circular orbits by proving that planets move in ellipses with the Sun at one focus. His second law revealed that planets sweep out equal areas in equal times, moving faster when closer to the Sun. His third law established a precise mathematical relationship between a planet's orbital period and its distance from the Sun. Kepler's laws transformed planetary motion from divine guidance into precise mathematical description, shifting astronomy from a descriptive phase to an explanatory one. Simultaneously, Galileo Galilei used his handmade telescope to provide empirical evidence for the heliocentric theory. He observed craters on the Moon, proving it was not a perfect celestial sphere. He discovered 4 moons orbiting Jupiter, proving not everything revolved around Earth, and he observed the phases of Venus, which only the heliocentric model could explain. These findings dealt a fatal blow to the geocentric view. In the 17th century, Isaac Newton synthesized these works into a classical mechanical system. He proposed the law of universal gravitation, stating that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton's framework unified the motion of falling objects on Earth with the orbits of planets in the heavens, viewing the universe as a vast, predictable machine. Under his theory, the universe was considered infinite and static, with absolute time and space. This deterministic view reigned for 2 centuries until the 20th century brought a new revolution. In the 1920s, Edwin Hubble observed that light from distant galaxies was redshifted, meaning they were moving away from us. This discovery, known as Hubble's law, revealed that the universe is expanding, overturning the idea of a static cosmos. At the same time, Albert Einstein proposed general relativity, describing gravity not as a force, but as the curvature of space-time caused by mass and energy. This provided a new framework for cosmic evolution. These breakthroughs led to the Big Bang theory, which suggests the universe began in an extremely hot, dense state and has been expanding and cooling ever since. The discovery of the cosmic microwave background radiation in 1964 provided the afterglow evidence needed to make the Big Bang the mainstream model of cosmology. However, even the successful Big Bang theory faces challenges like the flatness problem, the horizon problem, and the monopole problem. To solve these, the inflation theory was proposed, suggesting a period of exponential expansion in the very early universe. Yet, even greater mysteries emerged with dark matter and dark energy. In the 1970s, galactic rotation curves suggested the existence of invisible dark matter providing extra gravity. By the late 20th century, observations of distant supernovae revealed that the expansion of the universe is actually accelerating, driven by a mysterious force called dark energy. Today, we know that ordinary matter makes up less than 5% of the universe, while dark energy and dark matter account for the rest. These mysteries have led scientists to explore even deeper possibilities, such as the global rotation of the universe. The concept of a rotating universe has a theoretical basis in general relativity. In the 1940s, Kurt Gödel found a solution to Einstein's equations that described a rotating universe where space-time is twisted, even allowing for closed time-like curves. While the Gödel model doesn't match our expanding universe, it proves that global rotation is mathematically possible. Such rotation would involve the dragging of space-time itself, potentially creating effects similar to centrifugal or Coriolis forces on a cosmic scale. Scientists are now searching for observational evidence of this rotation in the cosmic microwave background, looking for spiral polarization patterns or specific directional anomalies. Although the universe appears highly isotropic, researchers are using advanced probes like the Planck satellite to find any subtle hints. Furthermore, the large-scale structure of the cosmic web and the emerging field of gravitational wave astronomy might provide new windows into whether the universe possesses an inherent angular momentum. If a global rotation is ever confirmed, it would require a revision of the cosmological principle, which assumes the universe is the same in all directions. As we move forward, the search for specific signals, such as B-mode polarization patterns in the CMB, remains a vital task for falsifying or confirming these rotating universe models, bringing us ever closer to the true nature of cosmic motion. To test the hypothesis of a rotating universe, scientists are developing and utilizing various advanced observational methods, with the precise measurement of cosmic microwave background polarization being one of the most critical pathways. The polarization patterns of the CMB can be decomposed into two types, E modes and B modes. E modes, which arise from density fluctuations and velocity fields, have already been accurately measured by detectors like the Planck satellite. B modes, however, are far more elusive. They may be caused by gravitational waves from the early universe or generated by specific anisotropic cosmic models, including those featuring a rotating universe. Future next-generation CMB experiments, such as the ground-based CMB-S4 telescopes and upcoming space missions, will detect CMB B-mode polarization with unprecedented sensitivity. Their data will be pivotal in testing rotating universe theories. Additionally, further analysis of galactic kinematic data will provide vital clues. By more precisely measuring the rotational velocities of distant galaxies, their orbital speeds around galaxy clusters, and their collective motion relative to the CMB, scientists can search for faint signals of global cosmic rotation. For instance, if the universe is rotating, galaxies in a specific direction might exhibit a collective motion preference. Statistical analysis of motion data from millions or even billions of galaxies may reveal this extremely subtle global rotation. The gravitational lensing effect could also serve as a tool for testing a rotating universe. When light passes through massive celestial objects, space-time curves, causing the light path to deflect and form gravitational lenses. If the entire universe is rotating, this rotation might leave a unique imprint on gravitational lensing images, such as minute distortions in the shapes of distant galaxies or discrepancies in the intensity of the lensing effect across different directions. These are incredibly faint effects that require extremely sensitive equipment and sophisticated analysis to capture. Looking ahead, the emergence of new observational facilities and technologies will undoubtedly provide unprecedented opportunities. Large infrared telescopes like the James Webb Space Telescope can observe more distant and earlier galaxies, helping us better understand the large-scale structure of the early universe. The soon-to-be operational Square Kilometer Array Radio Telescope will map the distribution of hydrogen with unrivaled sensitivity and resolution, providing a clearer picture of cosmic structures and motion patterns. Perhaps most exciting is the maturation of gravitational wave astronomy. Space-based detectors like LISA are designed to detect gravitational waves on a cosmic scale. If the universe possesses a persistent global rotation, it could theoretically produce an extremely faint and continuous gravitational wave background. This pattern would differ from the transient gravitational waves produced by black hole mergers. If LISA can detect this specific mode of gravitational waves, it would provide revolutionary direct evidence of global rotation by detecting ripples in space-time itself rather than just electromagnetic signals. If the rotating universe model is eventually confirmed, it will offer entirely new perspectives for solving hidden challenges in the standard Big Bang model. For example, it might naturally address the flatness problem by allowing rotation effects to drive the universe toward flatness during its evolution. It could also provide an alternative explanation for the horizon problem by linking regions that were previously thought to be disconnected. Furthermore, rotation might have an intrinsic connection to the origins of dark matter and dark energy. Some bold hypotheses suggest that cosmic rotation could be linked to the dynamics of dark energy or that rotation itself is a macroscopic manifestation of dark energy. If these ideas are verified, the theory of a rotating universe would not merely be a correction to the standard model but a profound revolution in our worldview. It would also alter our understanding of cosmic symmetry and anisotropy. We have long assumed the universe is isotropic on a large scale, but global. Rotation would imply that the universe is not perfectly symmetric and possesses a unique axis of rotation. This discovery would touch upon the deepest principles of physics, potentially offering clues to long-standing puzzles such as the unification of general relativity and quantum mechanics into a theory of quantum gravity. A rotating universe would serve as a unique testing ground for quantum gravity theories like string theory and loop quantum gravity. String theory suggests that fundamental particles are tiny vibrating strings in higher dimensional space-time. A macroscopic rotation might correlate with specific vibrational modes of these strings. Loop quantum gravity, which attempts to quantize space-time itself into a network of loops, might find parallels in the spin properties of space-time. Beyond this, cosmic rotation may be tied to the origins of the universe and the pre-Big Bang state. If the universe rotates, it raises questions about whether this motion is a remnant from a previous cycle in a cyclic universe model or an integral part of the mechanism that triggered the Big Bang. This rotation might even influence phase transitions in the early universe, affecting the distribution of matter and energy. Furthermore, it could influence the ultimate fate of the universe, whether it ends in a big crunch, a big rip, or eternal expansion by acting like a cosmic gyroscope that stabilizes expansion. Perhaps most intriguing is the potential link between cosmic rotation and chirality, the property where an object cannot be superimposed on its mirror image. In particle physics, neutrinos exhibit a specific chirality, a fundamental feature of the weak interaction. On a macroscopic level, if galaxies tend to rotate in a specific direction, it might suggest a global chiral imbalance. This could even extend to the mystery of why life's building blocks, like amino acids and sugars, possess a single specific chirality. This cosmic rotation might have provided the selective pressure for the homochirality of life on Earth. Humanity's exploration of the cosmos is an endless epic, moving from primitive curiosity to the sophisticated theories of today. The theory of a rotating universe is a captivating chapter in this journey, challenging our perceptions of symmetry and pushing the boundaries of science and philosophy. Every breakthrough in cosmology redefines our place in the universe, shifting us from the perceived center of the world to being part of a vast, evolving, and perhaps rotating reality. Whether this hypothesis is confirmed or falsified, the pursuit itself enriches our understanding and inspires the next generation of explorers to uncover the deeper mysteries of the cosmos. That concludes our journey for today. I wish you wonderful dreams and a beautiful day ahead. I will see you in the next episode.